welcome everybody. So for today's seminar, we have our very own Matteo Piani, and well, you all know him, but like this is a short bio. So he did his bachelor's and master's in Bologna, and now he's doing a PhD here in CENTRA under the supervision of Javier Rubio. And his research topic is in the relation between the Higgs field and gravity. And well, the stage is all yours.
Thanks a lot, Edgar, and thanks, Justin, for taking care of everything. So, hello, everybody. First of all, thanks for being here. Very happy to be on the other side for one time and change the perspective, and also to have the opportunity to talk about some things that we do in CoStar, hoping that you might like some of them. Today, I would like to talk about one of our recent work with me and Javier about an inflationary model called Higgs-Dilaton in the context of Einstein-Cartan gravity. So, without further ado, let's start. So this is the outline of the talk. The first part I will do like a small review of inflation, and in particular Higgs-Inflation, and in the context of Einstein-Cartan gravity. This is some is based on our work done from other people, but still is just as a proxy for the second part, in which I will address the actual model that we're using, that is the Higgs-Dilaton one. And if I have some time left at the end, I would like to say something about what we are doing now. That is what happens after inflation, and there are some very nice features that we can discuss. So, first part, Higgs-Inflation. First of all, let's start with what is inflation. For those who know already, it's just probably a boring reminder. For those who don't know, it's a super quick crash course. So inflation is a phase of accelerated expansions that takes place in the very early universe. So this is like a map of the universe. We are here now, and this is like basically the first thing we can track back to is inflation. Why do we need inflation? Well, we have observation that our universe is homogeneous and isotropic on large scales. And indeed, we describe with this Friedman-Demet-Robertson-Walker metric. That is what is described an isotropic scenario. The natural question could be also why. We observe the cosmic microwave background, and we have like small differences, but fluctuation of order 10 to the minus 5 respect to the 3 Kelvin temperature. So how do we get there? And also we have a series of problems that I will not discuss here that inflation is solving. So to get there, what we want is an accelerated phase of expansion where this scale factor that tells us how 2 points are separated during time is growing exponentially with time. So the question now is, how do we get inflation? The most successful model so far is what we call single field slow roll inflation. So we have a scalar field with just a kinetic term and a potential, and it is minimally coupled to gravity. Usually what we are looking for is a potential of this kind, so something that has, yes, a minimum, but has a very flat region. And this is why, in order to have inflation, we need the dominant contribution of the energy density to be the one coming from the potential. So what we have is like some initial condition, and your field will be like slowly rolling down this plateau region, and at some point it will start rolling faster, so we will stop inflating. And the moment in which this will happen is when we break these two slow roll conditions that are basically just related to the derivative of the potential with respect to the scalar field that we call inflaton, by the way, and it is homogeneous also during inflation. How do we do inflationary physics? So, okay, we have the model, but we have to test somehow this model, or at least be able to put constraints. So what happens is that during inflation, we have quantum fluctuation of the inflaton field, and this can produce actually two kinds of perturbation. One is the curvature perturbation, and one are the tensor perturbation. This is just an approximated form in the inflationary scenario. So the quantity that we can actually measure are two.
One is this NS, that is called spectral tilt. And the reason for the name is basically that when this is 1, you get a fully scale invariant scenario. So all the scales are powered up in the same way. And the other thing that we can measure is the ratio of the amplitude of the two kinds of perturbation. But the most important thing is that these measurements are strictly related to the parameters that I was showing you before. Therefore, you tell me your potential, and I will tell you where you are. What does this mean? This means that we go to the amazing results from the Planck collaboration. We have here the tensor to scalar ratio on the y-axis and the spectral tilt on the x-axis, and we have these contour plots that are giving us constraints. So you take your inflationary model, you compute these two quantities, and you go in this plane, and you see whether you fall or not inside the constraints given by Planck. So these, by the way, are relatively old constraints. There were some more recent one from BICEP that are restricting these peak by a factor 10, I would say. We are, for the tensor to scalar ratio, we are order 10 to the minus 2 now. So as you see, a lot of part of the parameter space is kind of ruled out. We really have to be 10 to the minus 2 in the tensor to scalar ratio. But the reason I chose to put this is to show that we have, in principle, many models of inflation. So these models are not necessarily telling you what is the inflaton, but are rather giving you behaviors of different inflationary models. And the fact that you have not single prediction, but rather lines, means that usually there is at least one free parameter, because on one side you want to be generic, and on the other side you want to kind of follow the experimental constraint and keep lowering your theory so that you always fall inside there. So, natural question, where is the inflaton? We are advocating a scalar field that we don't know what it is. This is a paper from 2013, if I'm not mistaken. It's called Encyclopedia Inflationaris, where they are looking at several models of the time. And as you can see, there are a lot. But there is one that is particular, and that is described as a zero parameter model. So a model in which you have actually no freedom to move in the plane that I was showing you before. And this model is Higgs-Inflation. So the way of reasoning is very simple. We are looking for a scalar in order to have inflation. We look at the standard model, that is all the particle content that we know, and we have only one. So the choice in this case is relatively simple. Let's try to use the one we know, and let's try to see if we can have inflation. So what I was calling phi now becomes h, because it's the x, and this is the standard model potential, a classical symmetry breaking scenario. And for the self-coupling of the x, we take the parameter by using the renormalization running at the inflationary scales, and we get there is something order 10 to the minus 3. First answer, you cannot inflate with that. And the very simple reason is that when you have quartic potential and you give the scale, you are fixing a tensor to scalar ratio, and spectral tilt are out of observational bounds, so there is no way to do with the simplest configuration. But it doesn't take much to actually get something that works, and what we need is a non-minimal coupling to gravity. So gravity can be the answer to turn the X into the inflaton. So we take just simply this sign that we have to determine by inflationary physics. Here we have the Higgs, and it's going to grapple directly with the Ricci scalar. Now we have another problem. Which gravity do we choose? So it's kind of known that there are different ways to formulate a theory of gravity, and they are all equivalent in the sense that you have to give up on, you can put to zero one of these quantities, so like metricity, torsion, and curvature, and this is always enough to get some kind of theory that is equivalent to GR, but it changes in as regards of geometry and the choices of the fundamental degrees of freedom. So as you see, GR is kind of overdetermined in a sense, because you are asking both no torsion and metricity. But there are other formulations like the Palatini and the Einstein-Cartan in which you just need one of those two. So as I was saying, these theories are equivalent. So you take the theory and you can always recast it in a form that gives you always the same prediction for purely gravitational phenomena. Now, this is not true in the moment we introduce this non-minimal coupling. This is completely breaking the generality between the theories. And the simplest way to see it is we can do a comparison between the metric and Palatini cases that have been extensively studied in the literature. So what you can do is just do a rescaling of the metric by this conformal factor that is exactly the prefactor that you have in front of the Ricci scalar, and go in what we call the Einstein frame. So you are decoupling the Higgs from the Ricci scalar, but now at the expense you get a different potential and a kinetic function in front of. Yes.
Sorry, but I have a question about the previous.
Yes.
In the middle of the surface.
Yeah.
But all of these conditions satisfied significant. You have R equal 0, G equal 0, and not the G. So is it really inevitably flat?
No, but flat means it's like you're forced to be impossible. You don't I think.
Right.
Yeah, I mean, it's like.
But for the Schwarzschild space-time, all of these Schwarzschild would be in the middle.
But I don't think you can have Schwarzschild there.
Oh, it's
Yeah.
That answers my question. Thank you.
Okay. And as I was saying, we get a kinetic term that is what is actually discriminating between different formulations. So here, for example, I have the comparison. This is the kinetic term for the metric case and the Palatini case. Very important, this non-minimal coupling depends on the formulation. Basically, what we do is we go to the inflationary potential and we see what are the conditions to match the correct shape of the power spectrum for the CMB, and we can uniquely identify this psi in this way. And it's very different. I mean, there are 4 orders of magnitudes in this case. But what is more important is that the predictions for the inflationary parameters are different. In particular, now I was not writing it, but this n is what we call number of equals, that roughly is just how much inflation lasts. So it's just a way to measure time. Low number of equals, short inflation, large number of equals, long inflation. Generically, we use kind of something between 50 and 60 because there are uncertainties related to what is happening after the inflationary phases, but this is not relevant now. So as you can see, the prediction for the spectral tilt is the same. And this is like the same, for example, that you get in the Starobinsky model and many models like this. But the prediction for the tensor to scalar ratio is rather different. In the metric case, this is order 10 to the minus 3. So this is very close to the upcoming CMB, to the bound that the upcoming CMB experiment should reach. So it's in the window for our next discovery, if it's really at that value. The Palatini case on the other side can go up to 10 to the minus 11. So it's basically 0. It's something we cannot detect, and even futuristically, or as far as I know, there are no ways to detect it. Now let's see the Einstein-Cartan scenario. So what is different from the others? Just some features, first of all. In Einstein-Cartan scenario, we take the connection and metric to be independent variables. We have a non-vanishing torsion, as I was showing in the plot before. And one of the, in my opinion, really cool thing about Einstein-Cartan gravity is that it's a theory that can be obtained by gauging the Poincare group. And this means that we have 4 fundamental forces. 3 of them are gauge theories. And it's like, okay, maybe we can even say that gravity is a gauge theory. This would be really nice to put just all the forces on the same footing. And lastly, one very interesting feature of this scenario is that you can naturally introduce fermion into the theory. But it's something that I'm not going to talk about because it's not relevant for inflation. So what is giving the difference with the other 2 formulations is that now we have a connection that a priori is not symmetric anymore within the lower indices. And so we have a non-vanishing torsion tensor. This creates problem in the build of the action, however. Problems in the sense that you have to make some choices. So what we have for sure is the Einstein-Hilbert term, the usual one, where we add the non-minimal coupling. Then what we need is the term for the scalar, because we have a dynamical scalar with a potential. But then we can choose other operators, because now there is a non-vanishing torsion. So what we were doing, and also other people, the approach decided is not to take operators with mass dimension bigger than 4, and try to avoid every way to have extra degrees of freedom in the gravitational sector. So we just have the two polarization of the graviton, and no like massive tensor modes or whatsoever. So this is common to also with the metric and Palatini case. But now we have two extra operators. These, I don't know if any of you are familiar with these. These are called Holst and Niemann term. So the Holst term, as I was saying, now the connection is not symmetric anymore. So the Riemann tensor is losing symmetry properties with respect to these indices, and we can contract it with an antisymmetric tensor. And also we can add a minimal coupling now, because this is what we are doing. So for the rest of the talk, just to be on the same page, I'm going to refer to this as non-minimal coupling, and although it's improper, I will call this kind of coupling topological, just because this one is a topological term, this one is not, but it's just to make the presentation and the flowing better. So we have an extra term. That is something that if you are familiar with loop-down gravity, apparently it appears here and there with this parameter that is called the Barberi-Mirzi parameter. And then we have a topological term that in principle, what you usually have is that this is disappearing. It's just a, yes?
Yeah, so I guess when you say it does not vanish, do you mean that it contributes to the field equation?
Well, this should give a boundary term, but when I put a field and non-minimally coupled, of course, in the integration by part, I get some extra contribution and it's not disappearing anymore. So these are the two things that we have been considering. And in the single field case, what we want to do is, first of all, rewrite the action in something that we can handle better, because when you want to do inflation, keeping stuff in this kind of expression is not very comfortable and useful either. So to rewrite the action, we have to do two things. First of all, we have to switch to the Einstein frame, as we were doing before. So we do again a wild rescaling of the metric. But second, we can remove the dependence of torsion of the torsion by splitting the connection into the torsionful and torsionless part. Then what happens in this particular theory is that torsion is non-dynamical, so we can solve for the torsionful part and plug everything back into the action. At the end, what we get is the same thing we had before, but now we have a rather more involved kinetic function, but the potential is exactly the same. So what they were doing, people studying this model, is considering, first of all, the two cases separately. And now I'm just going to present the results, because the numerical results, because the analytical one would require a lot of discussion, and we will see with our model actually what happens. So this is the Holst inflation. So as you see, you have your Barberi-Mirzi parameter. You don't have the topological coupling of the Niemann term, but you have another coupling for the Higgs and the standard one. And what they were finding is that basically, if you see, the value of this psi is constrained, at least in this part of the parameter space, to be 10 to the 7. That is exactly the Palatini value. So for what it concerns this part of the region, we get exactly the same prediction as in Palatini gravity, plus we get something extra. But now we go to look at the tensor to scalar ratio, that is what we want to constrain. And here we get a super low value that we are never able to constrain. But here we get actually something that now from this cover is not easy to see, but it's almost 10 to the minus 2. So it's very close to the current observational bounds and very likely to be excluded by a future experiment. Now, the most interesting one is actually Niemann inflation, because Niemann inflation provides a scenario in which you can smoothly transform from metric scenario into the Palatini scenario. So it's really something in between, just by the change of this coupling sign, so the topological coupling of the Higgs. So we have a region in which the non-minimal coupling is small that will give you some kind of quartic potential. So basically, we are not modifying the potential of the Higgs. Then we have this transition, and we have a point that is exactly when these two couplings are equal, in which we recover exactly the metric theory. Then we have a transition scenario that we can predict what is going to happen analytically, but still we don't have maybe a full insight with a full potential. And then we have all this part in which your topological coupling starts becoming negligible when compared to the standard one, and we get completely the Palatini prediction. And the interesting thing to see here is that there is a correlation clearly between the value of this parameter psi and the tensor to scalar ratio. So as we will see later, it's not like there is a random mixing of these two couplings, but there is something clearly that is correlating these quantities in a certain way. Okay, now I will go to the second part of the talk, and I will talk about the model that we were actually looking into it. But before doing that, I had to introduce a bit of scale symmetry. That is the new ingredient we put into this scenario. So scale symmetry, if you want to see it purely mathematically, is just this, is symmetry under dilatation. So you change the metric with a factor sigma, and all your fields in the theory will scale like this with a certain dimension of the scaling that depends on the kinds of field. The main consequence of scale symmetry is that we are removing all scales from our model. But this, of course, cannot be forever, because here now we have the Planck scale, we have the Fermi scale, so there are mass scales in physics. It's not like we can rid of it without consequences. So we need this to be a spontaneously broken symmetry. So we have a regime in which this symmetry will be active, but at some point we need to break the symmetry and generate these scales. Now, the motivation for implementing scale symmetry, because you may ask, okay, why do you want to put this extra symmetry in the model? There are some motivation. First of all, one is related to the Higgs boson. There is this long-standing problem that some people don't even consider a problem, that the Higgs boson mass is unstable under radiative correction. So what we can actually do is take a scale invariant scenario, which will put the Higgs mass to 0 and prevent completely the radiative correction to move it from 0. So the Higgs will take a mass just from the spontaneously broken symmetry of scale invariance. Second thing is that all the scales in the model, in this case is just Fermi scale and Planck scale, will get a common origin. So it's always nice to say that you have scales that come from the same thing, although they are very different. Another motivation is that if you take the usual standard model plus gravity, just the action like that, when you go to large field values of the Higgs, that are the ones relevant for inflation, you get a model that is approximately scale invariant. So a good guess that you can give is like, okay, maybe this is an underlying symmetry of my theory and it's not just something that is appearing. And finally, what is maybe more interesting, when we put the Higgs mass to 0, we can enable a mechanism that that can allow to generate the Fermi scale through gravitational instantons. So this is like really, I have gravity and I generate a Fermi scale with a purely gravitational phenomenon. And this has been studied years ago, but it is a very interesting mechanism. Yes?
Can you say for an outsider, can you say why that instability that you said some people don't think is a problem, they don't think that it's a problem, and if you do think it's a problem, say why it is a problem?
The problem is that I keep changing my mind. There were some papers recently, so basically the fact is that to see this instability in the first place, you have to introduce the so-called bare masses of the Higgs. And some people argue, maybe rightfully, that that is not physical. So those instabilities, I mean, there are ways to do the computation without having to fine-tune everything and do weird things. But then the question is, so is that physical or not? Is debatable. I mean, depends on your standpoint. But one of the consequences of putting scale symmetry is that we get an extra degree of freedom. Of course, we have a symmetry, we break spontaneously, so we have to get the corresponding Goldstone boson. Then in this case is the dilaton, or dilatation, of course. And in our particular scenario, what we get is 6 free parameters. That is something that maybe you don't enjoy at the beginning, but this doesn't mean that all 6 of them are actually relevant, or we can find combination of them that are relevant for our purposes. So now I start a bit with formulas. I apologize in advance, but they are there. I cannot avoid writing them. So the scenario is exactly the same as before. We have the action with the Einstein-Cartan. Now we have 2 fields. We have 2 scalars. And again, a potential that is kind of the same as before. But now, instead of having the expectation value of the X, we have another field. Then we have the Holst. Again, the only difference is that we are parameterizing basically the Planck mass with this tau, that is again a non-minimal coupling, and chi-squared. So basically, the dilaton together with this non-minimal coupling is going to give you the Planck mass once you relax to the minimum of its potential. Then again, we have the Holst and the Nierian term. Now, let me remark something about the Holst term. The 3 parameters in the Holst term are 3. This notation, I think, is very misleading, but since we wanted to compare with other things in the literature, we decided to follow this notation. But the 2 parameters that are independent are gamma bar and psi gamma, because this tau is the same appearing in the other term. So now, same thing. We want to go to an equivalent metric formulation. But this time, things are rather more involved. First of all, we have 2 fields. So instead of getting a kinetic function, we will get a kinetic matrix. Kinetic matrix means that we have also some mixing between the kinetic terms of the fields, and everything is becoming kind of more complicated. As you see, I mean, I try to simplify, but if you try to put this stuff in the matrix, and everything gets bigger and bigger, and it's very hard to figure out something just by looking at that. Moreover, another problem related to this is that now our potential has 2 fields. And when we do inflation, we are always a bit scared when we see a potential with 2 scalar fields, because we can have some stuff that we don't want, namely like isocurvature perturbation or non-Gaussianities. And these stuff are related to the fact that you have an inflaton that is moving along a trajectory, but now you have also a perpendicular trajectory, and you can start moving there. And it's something that you don't want. It's heavily constrained by observation. That's why people usually talk about single field inflation. Okay, so we say that this is rather complicated, and we do not really want to address something like this brute force. So let's try, first of all, to notice something, that this particular matrix in the large X limit and at leading order in the dilaton coupling, so if I assume tau and tau eta to be small, becomes maximally symmetric. And the Gauss curvature of this manifold is given by this expression. So right now we take this information, we put it apart for a moment, and we will recover it later.
So is this, so I guess that Gauss curvature, it's in the field space.
Is in the field space, exactly. It's not the metric one. So as I was saying, we have 2 fields, and we really do not want 2 fields in our model. But we have something to help, because we added an extra field, but we also have an extra symmetry, that is scale symmetry. So what you can do is take another current that is associated with this scale symmetry and compute it. And you can see that there is always a kind of smarter change of variables that will give you a current that decouples in this way, in which you have a function that depends on one field and the derivative of the other field. So what this is kind of telling us is that when we want to study inflation, the inflaton is not really the Higgs itself. And so the dilaton is not the field chi that I was writing you before, but this is what we can call the physical dilaton, and this is what we can call the physical inflaton. Of course, once we are going to the minimum of their potential, these fields will reduce respectively to h and chi. But when we are in inflationary scales, this is not true. This has very important consequences, as we can see in this plot. So basically, the motion of your field is constrained. You see, there is a constraint. It's not like h and chi can take whatever value they want during inflation, but they are forced along this trajectory. That this is from the metric case. This is not our case, but when you analyze it, you find it exactly the same kind of figure. And we are in this kind of elliptical trajectories that are constrained for our field. And the nice thing is that we don't care even if we start out of the slow roll condition. So even if we take a field that is moving like we start from here, it's moving like really fast, is moving backwards, forwards, we do not care. In the end, this is going to be dumped very quickly and is going to fall down in an inflationary trajectory that is just one of these slow roll one. So we did the same thing. We decided to analyze Holst inflation and neon inflation separately. And we did two things. So first, some kind of blind Monte Carlo approach, just to see where we have to look. And this is the result. So basically for this approach, we select how long inflation has to last. And we just require the amplitudes of the inflaton potential to match the one of CMB observation. So the observables that we have are left completely unconstrained, so we just want to see what we get in different regions of the parameter space. Now, as I was showing for the single field case, we have some kind of fixed value in a region of the parameter space that is the one again of Palatini inflation. So this is already telling us that there is a region that is basically giving the same kind of result as the single field one. Then we have also the other region they were finding, but we found something more that unfortunately is completely out of the observational bound, so there is probably nothing too interesting to look in there. But let's go to the analytical part and try to see if we can actually say something more. Well, the principle, when you have these kind of models, I'm going back to this, would be first of all to diagonalize this matrix, so I can decouple the two kinetic terms. And then once I have done this redefinition into these fields, now I have that one field that is the inflaton is appearing in the potential. The other field that is the dilaton is not appearing in the potential, of course. That was the purpose from the beginning. And also, very important, this dilaton is going to have only derivative couplings with all the matter fields, so it's not something that we can observe like in accelerators. These couplings are heavily suppressed. Now, we have a kinetic term. So the first thing one will try to do is to canonically normalize. So do another field redefinition, absorb this k theta into the definition of theta itself. Your potential will change accordingly, but then we can use the nice formulas we had before and find all our observables. Turns out this is not very simple. If you look just, to get Holst inflation, you just have to put all these tau eta and psi eta to 0. And trust me, it's not helping too much in simplifying the expression. Of course, it's simpler, but still very complicated to treat analytically. But there are tricks that we can employ, and we did. So on the same kind of approach, following the same kind of approach as in the metric case, we were looking for some kind of trajectories in this plane, and we tried with this change of variables. Let's say it's a since a relatively good change of variables. So our inflaton now is a combination of the Higgs and the Dilaton, again, just with this conformal factor that I was writing before. And it takes a very interesting shape, the kinetic term. So as you see, you have a pole in theta equals 0, first of all. Then you have yet another pole in theta equal minus c over kappa h, where this kappa h is the Gauss curvature I was telling you before, but just in the Holst case. So basically you put all the other terms to 0 and you get this Gauss curvature. And we have also another pole in theta equal 1, plus this f gamma phi is a regular function. So what happens is that when you move with your inflaton, so with your theta, and you encounter one of these poles are going to stretch your potential. And this is what gives you the really flat potential that you want to see. So this pole, first of all, is not relevant because this is what we call an Minkowski pole, is the pole that we have in the minimum. So we don't care while we are in inflation about that. These two poles on the other side are those that really gives you the phenomenology of the model. And it's not the first time that this is appearing in inflationary models because it's the exact same thing that happens for the metric formulation. So if we remove this term that is going to be subleading and this term that is regular, we are left with just these two terms. And in the limit in which this c over kappa h is very small, so in which the two poles are not very separated, the one is 0 and one is almost 0, we can get very nice prediction for the tensor to scalar ratio that is just related to the curvature of the manifold and to this parameter that at the leading order is just the Dilaton coupling. So again, we have a lot of things like this psi gamma. As you can see also, you can expect kind of from this parameter space is completely irrelevant. Like we are here, we can move vary psi gamma and we get the same result. It becomes relevant here, but this is where really the physics of this is coming out. This is something that is working only in what I was saying before, that is the maximally symmetric limit. When we go in this region of the parameter space, we are not in the limit, and we are very lucky because the observables there do not fall in the observational bound, so we really don't care about that. We just focus on this, and for this we have very nice prediction. As you can see here, there is a comparison from the numerical scan that is done only for large values of size. So of course we have to constrain to this kind of surfaces, and the analytical prediction that is given here and is working kind of perfectly. When we go to very small Dilaton coupling, we recover the prediction that was made for the single field case and for all these other models. That is this formula for the spectral tilt. And this also is actually working for higher values of the Dilaton coupling tau, but the problem is that you quickly encounter the observational bound of the spectral tilt. So again, we do not care into looking in something that is really larger than 10 to the minus 3, let's say, for the Dilaton coupling. And now, again, the most interesting one, that is the Yang inflation. So in this case, the structure is similar, but also rather different. As before, we have the same poles, but now we have something extra. And this is quadratic. Of course, you have theta here and here, but it becomes cubic. So it's giving completely a different phenomenology in the regime in which this pole can be actually explored by our inflaton field. So we go again to our very trustful and reliable Monte Carlo simulation, and we check what is happening. And we see that, I don't know if you remember the plots I was showing before, but this kind of profile, lateral profile, is exactly the same thing that we have in the single clip case. So in principle, it seems that it's just a projection of the other plot, and it is, as long as this Dilaton coupling, the topological one, is not very large. When these become to be dominant, however, we start seeing like new regions, and we have something very interesting that usually don't happen too much in inflationary models. We can go to smaller values of the spectral field, that is kind of easy to obtain. But what is harder is going to higher values of the spectral field. And here we are getting closer and closer to 1. We cannot get to 1, of course, otherwise it will be a super big model if we can cover everything. But it's very, this is what is really distinguishing from the other cases. And again, as before, the tensor to scalar ratio is showing some kind of nice dependence just on this coupling. And the thing is coming actually from here, because the tensor to scalar ratio, the Higgs no-minimal coupling is what is regulating this Gauss curvature. And also I want to point out that this is not a typo, in the sense that in this formula, what is appearing is the Gauss curvature of the Holst term. Because, well, while it would be super nice to decouple and get the Nye-Yang one, it seems like the formula are not just like that. And we have this, so it's not super evident from the formulas that there is the analogy is taking place. In case you are interested, you are more than free to read all these things that are appearing inside here, but they are not very relevant for the discussion. So what is going on physically? Because we have, as I was showing you, we have something new that is appearing. And when we go again to the plane that I was showing before at the beginning, this R and S plane, there is a very nice interpretation of these two results. There is basically a quadratic pole in the kinetic term and a cubic pole in the kinetic term. So these poles in the kinetic term have been studied already, it's not something new. But what is new is that in this model, they are appearing kind of out of nowhere, we can say. So usually what you do is you study pole inflation, but you don't know what is the inflaton. You say, if I have that kinetic term, I get that. But in our case, we are getting a cubic pole that is, I would just say unusual, but probably in these models usually is not there, the cubic pole. And this we can see again, thanks to our beautiful Monte Carlo simulation, these two trajectories are the same thing that I was showing you before. So basically, the main difference between Einstein-Cartan and metric and Palatini formulation is that in this case, the presence of extra couplings and extra operator is giving us freedom. So if you want, can be something good, can be something bad. You are less predictive because you are not giving a single value for these two things, but you're rather giving a family of values that you can take based on a parameter. And in this case, what that parameter is, in one case is the Gauss curvature, and in the other case is this inverse residue of the cubic pole that are making you move a lot along these attractors. And in terms of parameters, what is discriminating between these two attractors is the value of the Dilaton coupling. And this is clear also from these plots, for example, like when you increase the coupling. So the cubic attractor would be like, imagine moving in a trajectory like this, and the quadratic one in a trajectory like this one. So to conclude, the Higgs-Dilaton model is very nice. It works also in Einstein-Cartan gravity, and we can contain the metric and Palatini scenario as particular cases, but also have a richer phenomenology. Also, we have seen that the prediction are quite remarkably boiling down to just geometrical properties of the kinetic field manifold. Holst case reduced to Palatini, and Nye-Yang can do both things and still be incompatible with data. And this cubic pole is something quite unique. And thank you for the attention.
Right. Thank you, Matteo, for this enlightening talk. Do we have any questions from the audience?
If we compare the Einstein-Cartan theory with the standard general relativity,
Yes.
which new features the Cartan theory has to theory in inflation?
So the real new feature, well, the things with Einstein-Cartan is that if I don't put these operators, are the new things that you can say, okay, for some reason these couplings are zero and these operators are not there, you get the Palatini prediction. So you don't get general relativity. You get general relativity in the limit in which this thing is zero and this coupling is the same as the one in the Einstein-Hilbert action, but otherwise is not general relativity. It's like the prediction are different. You get this thing, you have free parameters, so you are kind of free with the prediction in a sense. In the other case, you have a single prediction. This one is standard general relativity, what we call the metric case. And for this case, you have single prediction. The value of the minimal coupling is fixed, so we know there what happens. But in the Einstein-Cartan case, unfortunately, these new operators are bringing freedom to the theory. So as long as you check one at the time, it's like one parameter freedom. So it's something that in principle you can kind of constrain, but you don't have a unique prediction in that sense. I don't know if this answers your question.
Any other question?
Yep.
Are you looking into Einstein-Cartan for any particular reason?
Yes. The particular reason is that this doesn't work well for inflation. This was studied already, and this also. So, no, jokes apart. The real reason is that the interesting part, there is one that is purely theoretical, and at least for inflation is not bringing anything new to the game, but it's because just the fact that you can get gravity as a gauge theory for me is super cool. And the other thing is that you have fermions that are naturally introduced in the theory because the energy momentum tensor, you have the antisymmetric, it will be antisymmetric and you can couple with torsion. So now I was not writing here, but actually when you rewrite this theory, you get directly fermion interaction, like effective one for fermion interaction, and they are there. You cannot remove them. I mean, they are coming out of the theory basically. So let's say that is the reason.
Other question?
This theory is studied like a context, not phenomenology, like I know, so symmetry, Latin, or whatever.
I don't know much, but you mean the non-minimally coupled one? Because if I minimally couple, they are equivalent. So that they don't, not to my knowledge. Still, with the Higgs, there is not much sense in my opinion, because the Higgs, once it relaxes to its potential, what you have is that this term is completely subleading. I mean, this is 10 to the 36 GeV squared, and this is going to be 10 to the 4, 10 to the 11 GeV squared. So it's like 20 orders of magnitude suppressed. And you can excite the field a lot, but not that much to go back to inflationary scales and be relevant. So in my opinion, for like standard GR objects, without going to large value of these, there should not be, they're all Planck suppressed, all these effects.
Any other question? If not, I have one.
Yes.
So when you choose the conformal factor omega equal to 1 plus something with h, is there a particular reason why that conformal factor is chosen in that way?
Because yes, I want to. Where do I have it?
That
I want to remove this from
okay.
the action. Basically, it's just
Okay, so
that
that trick gets rid of.
I can get this. It's just to remove that from the
I
action.
see. And another question: this theory, does it admit like a well-posed initial value problem?
Okay, I don't see why not, because once I'm here, if I take this theory, I don't see why it should have problems. It's just gravity plus a scalar.
Okay.
Now, in the moment you allow for negative values of this, maybe. Some people have been studying, but just the phenomenological consequences. I don't know about the theoretical thing, but there are very good reasons also about stability of our universe for which this should be positive. So we haven't looked into negative values of the coupling, also because of this reason, because we don't have everything under control from theoretical point of view.
Any other question? Yes.
As you mentioned, that the series can be equivalent in some cases. In principle,
how one can distinguish the results, where they come from.
Ah, no, you cannot. In the moment in which you don't have these non-minimal couplings, these are actually equivalent. Like in this case, you exactly get the Einstein's equation. In this case, it's a bit more shady, but you still get something equivalent to GR. So you really don't see the difference. It's like a reformulation, a different choice of degrees of freedom, maybe a different interpretation if you want, but the observation are going to be the same. There is really nothing that, as to my knowledge, that can you make this thing, can you make to distinguish from this theory. The only way is to have these non-minimal couplings that in principle is fully consistent with the symmetries of the theory. So even if you don't put it, it should be generated by radiative correction. So it's not like illegal, it's not like put there because we like to, but it should be there in principle.
But in principle, it comes out that some prediction from the more complicated theory and from more simple theory inside.
Yes. Well, more complicated or more simple, I don't know if depends what you mean. I see them all equally complicated. Ah, okay. Yes, but this is not really more complicated. I mean, the action is the same. I can. So the action is the same as general relativity. Once I remove this general Planck squared over 2 coupled to the Ricci, the difference is that in one case, for example, this is not dependent of the metric. But once you go to the equation of motion, you find the equation of the connection for it. Like this is what happens in the Palatini case. So the metric and connection are independent, but then you find the equation of motion for the connection, and you find that this is the usually Levi-Civita one. So it's the same theory, just in one case you are giving the relation, in the other case you are finding with the equation of motions. And same goes for Einstein-Cartan.
So I guess I got a bit confused by your comment about this. So it's my understanding that if you have Einstein-Cartan and you have, I guess you consider the couplings to spinor fields.
Okay,
then
that
in
is
that case,
actually
you
you
can
are right. That is the difference. I was talking mostly about inflation, but that is a difference actually in principle. That is something that I don't know the reference, but has been studied maybe for the collapse, for example, because it can give you some kind of repulsive forces and our singularities. But I don't know much. I just know that that has been studied. Ah, also, yeah. Yes.
Maybe even one of my collaborators.
All right. So are there any final questions? If not, let's thank again our speaker.
If you enjoyed the video, like and subscribe.